Hello, and welcome back to the Sleep Lab. Tonight we are leaving behind the body, the bedroom, and even the ordinary rules of cause and effect, and drifting instead into the strangest, smallest layer of reality ever discovered, the quantum world. Most people go their entire lives never really encountering quantum physics beyond a vague memory of a cat that is somehow both alive and dead, or a half-remembered phrase about particles being in two places at once. And that is completely understandable, because quantum physics does not behave like anything in ordinary human experience. It was not built to make intuitive sense. It was built, slowly and carefully, over more than a century, by physicists who kept running experiments that refused to obey the tidy, predictable rules of the everyday world, until eventually they had no choice but to accept a reality far stranger than anyone had expected. Tonight we are going to walk gently through some of the facts about this hidden layer of existence that the vast majority of people never learn, not because the ideas are unknowable, but because they are rarely explained slowly enough, or calmly enough, for the strangeness to actually settle instead of overwhelm. There is nothing to solve tonight. Nothing to calculate. Just a quiet unfolding of one of the deepest mysteries the human mind has ever touched, offered slowly enough that you can let your thoughts loosen and drift right alongside it. It helps to say a brief word about why this particular corner of science tends to feel so uniquely disorienting compared to almost anything else you might learn. Most scientific discoveries, however surprising, still tend to extend or refine ideas that already feel intuitively familiar. Learning that the Earth orbits the Sun, or that germs cause disease, or that continents slowly drift over millions of years, each required a genuine shift in perspective, but none of them asked you to abandon the basic logical scaffolding your mind uses to make sense of the world moment to moment. Quantum physics asks something different, and something considerably stranger. It asks you to accept, at least provisionally, that a single object can genuinely exist in more than one state simultaneously, that the simple act of looking at something can change what that something actually is, and that two particles separated by the entire width of the universe can remain linked in ways that seem to defy ordinary cause and effect entirely. None of this is a flaw in the theory, and none of it reflects some failure of human understanding still waiting to be corrected. It is simply, as best anyone can currently tell, how the universe actually, genuinely behaves at its smallest and most fundamental scale, a discovery so strange that even the physicists who built the theory from the ground up spent decades, in some cases, quietly unsettled by their own equations. So if this kind of journey is worth your time, a like, a subscribe, or a thought left below helps this small lab keep its lights on for other sleepy minds finding their way here. But for now, there is nothing you need to do except settle in, let your body grow heavy, and let your mind wander gently into the smallest and strangest layer of the universe there is. Let's begin. For most of human history, and still in most of ordinary daily experience, the universe feels continuous and unbroken flow of space, time, energy, and motion, the way a river feels unbroken even though we know, on reflection, that it is made of countless individual drops. Quantum physics revealed something startling underneath that smooth surface. At the smallest scales, many quantities in nature turn out not to be continuous at all, but to come only in discrete, indivisible chunks, or quanta, from which the entire field takes its name. Energy, for instance, does not simply increase or decrease smoothly the way you might raise or lower the volume on a stereo. In certain physical systems, energy can only exist at specific, separated levels, jumping instantly from one allowed value to the next with nothing valid in between, the way a staircase allows you to stand only on individual steps and never on the empty air separating them. This discovery traces back to physicist Max Planck in the year 1900, who introduced the idea almost reluctantly, as a mathematical trick to solve a stubborn problem in the physics of heat and light radiation, never fully believing at first that nature was actually built this way rather than simply behaving as though it were for the sake of a convenient equation. It took years, and further work by Albert Einstein explaining a related phenomenon called the photoelectric effect, before physicists gradually accepted that this graininess was not a mathematical convenience at all, but a genuine, physical feature of reality itself. This idea alone, that the universe at its smallest scale is not a smooth continuum but something closer to a fine, granular texture, was disorienting enough to shake the foundations of 19th century physics, and it was only the very first of many strange discoveries still waiting to be found underneath it. It's worth pausing on just how reluctant Planck himself was to accept the full implications of his own discovery, because the story offers a small, human window into how genuinely disruptive this idea was even to the very physicist who first proposed it. Planck was, by most historical accounts, a deeply conservative physicist by temperament, someone who had spent much of his earlier career committed to the elegant, continuous mathematics of classical physics, and he initially treated the idea of quantized energy as little more than a calculating device, a useful mathematical fiction that happened to make the equations match experimental observations of glowing hot objects, without believing that nature itself was actually, physically built from discrete packets. It took years of additional evidence, including Einstein's independent work explaining the photoelectric effect using the same quantized picture of energy, before the wider physics community, and eventually Planck himself, came to accept that this graininess was not simply a convenient mathematical shortcut but an authentic, physical description of how energy actually behaves at the smallest observable scales. This reluctant, gradual acceptance is a pattern that would repeat itself again and again throughout the early decades of quantum theory, as one strange, unintuitive discovery after another forced physicists to slowly, sometimes painfully, abandon assumptions about reality that had felt completely secure and self-evident for centuries beforehand. One of the oldest and strangest puzzles in physics concerns something we interact with every single day without a second thought: light. For centuries, physicists debated whether light was fundamentally a wave, a rippling disturbance moving through space the way sound moves through air, or fundamentally a stream of tiny particles, moving in straight lines like miniature projectiles. Each side had genuinely compelling evidence. Experiments demonstrating interference, where two beams of light overlap and create alternating bands of brightness and darkness, seem to prove conclusively that light behaved as a wave, since only waves are capable of producing this kind of overlapping interference pattern. Yet other experiments, including the photoelectric effect Einstein explained in 1905, showed light knocking electrons loose from a metal surface in a way that only made sense if light arrived not as a continuous wave but as discrete, particle-like packets of energy, later named photons. For a long time, this appeared to be an unsolvable contradiction, as though physicists were being asked to accept that light was simultaneously a smooth, continuous ripple and a stream of individual, countable bullets. The eventual resolution, one of quantum physics' most genuinely mind-bending conclusions, was not to choose one answer over the other, but to accept that light is, in some deep and fundamentally non-intuitive sense, both at once, with its behavior in any given moment depending on precisely how and when it happens to be measured or observed. This principle, known as wave-particle duality, turned out not to be limited to light alone. Physicist Louis de Broglie proposed in 1924 that the same strange duality applies to matter as well, meaning electrons, atoms, and, in principle, every object in existence, including your own body, carries an associated wave-like character alongside its familiar particle-like properties, a claim experiments would soon confirm in ways that felt, to the physicists conducting them, almost too strange to be true. De Broglie's proposal, that matter itself carries a wave-like character, might have remained pure speculation had it not been confirmed remarkably quickly through direct experimentation. In 1927, physicists Clinton Davison and Lester Germer, working largely by accident while studying how electrons scatter off the surface of a nickel crystal, observed a distinctive diffraction pattern in the scattered electrons, the unmistakable signature of wave behavior, appearing exactly where classical particle physics would have predicted no such pattern should exist at all. This experiment offered direct, physical confirmation that electrons, long assumed to be simple, solid, particle-like objects, genuinely do carry an associated wave character, exactly as de Broglie's theoretical work had predicted just a few years earlier. The wavelength associated with any given piece of matter, according to de Broglie's equations, depends inversely on its momentum, meaning objects with larger mass and higher momentum, essentially everything in ordinary daily experience, have an associated wavelength so vanishingly, immeasurably small that wave-like behavior becomes completely undetectable and irrelevant at human scales, which is precisely why we never notice this strange duality in our own everyday interactions with the physical world, even though, at the deepest level of physical theory, it technically applies to literally everything, ourselves included. It's worth reflecting on just how strange it is, sitting with this idea quietly for a moment, that you yourself, in some deep and mathematically real sense, carry an associated wavelength as you move through space, however impossibly small and undetectable that wavelength happens to be given your own considerable mass compared to an electron. Physicists sometimes describe this as one of quantum mechanics' quietly humbling lessons, a reminder that the strange rules governing electrons and photons are not some separate, foreign set of laws applying only to a distant, exotic realm walled off from ordinary experience, but the very same underlying rules that describe the entire physical universe, including your own body, simply expressing themselves so faintly at human scale that they remain forever beyond the reach of direct, everyday perception, hidden not because they stop applying, but because their effects become vanishingly, imperceptibly small the moment enough mass and complexity enters the picture. If there is one single experiment most responsible for revealing just how strange the quantum world truly is, it is the double-slit experiment, a deceptively simple setup that has been performed and refined for over 2 centuries, first with ordinary light and later with individual electrons and even entire atoms. The setup itself sounds almost too plain to matter. A barrier with 2 narrow parallel slits is placed in front of a detection screen, and particles, whether photons of light or individual electrons, are sent one at a time toward the barrier. If particles behave the way ordinary objects do, like tiny marbles being thrown at 2 open doorways, you would expect each individual particle to pass through one slit or the other, landing on the screen behind in two simple clusters roughly aligned with each slit's position.
That is not what happens.
Instead, over time, an interference pattern gradually builds up on the screen, a series of alternating bright and dark bands exactly like what would be produced if each particle had somehow passed through both slits simultaneously and interfered with itself, the unmistakable signature of wave behavior, even though the particles are being fired one at a time, with no other particles present to interfere with along the way. This alone was strange enough.
What made the experiment genuinely unsettling to physicists came next.
When researchers placed a detector at the slit specifically to observe which slit each individual particle actually passed through, the interference pattern vanished entirely, and the particles began behaving exactly like ordinary marbles again, landing in two simple clusters rather than the delicate banded pattern seen before. The mere act of observing which path the particle took appeared to fundamentally change its behavior, as though the particle only commits to a single definite path through space at the precise moment someone actually looks. This result has been reproduced countless times, with increasingly sophisticated technology, and it remains, even now, one of the most genuinely disorienting findings in the entire history of experimental physics, precisely because it suggests that observation itself is not a passive, neutral act, but something that actively participates in shaping the physical reality being observed. Physicists have gone even further with this experiment in recent decades, developing a particularly striking variation called the delayed choice experiment, first proposed theoretically by physicist John Wheeler and later confirmed through actual laboratory demonstration. In this version, the decision about whether to measure which path a particle took is made only after the particle has already, in principle, passed through the slits, using clever experimental arrangements that delay the choice of measurement until the very last possible moment. Remarkably, the outcome remains exactly the same as in the ordinary version of the experiment. The interference pattern still vanishes whenever which path information is ultimately obtained, regardless of whether the decision was made before or after the particle passed through the barrier. This result deepens the mystery considerably, suggesting that the particle's behavior cannot simply be explained by imagining it somehow decides in advance whether to act as a wave or a particle at the very moment it passes through the slits, since the later decision, made after that moment has already passed, still appears to influence what happened. Physicists continue to debate the deepest philosophical implications of this result, but the experimental findings themselves remain remarkably consistent and well established, standing as one of the clearest, most rigorously tested demonstrations of just how thoroughly quantum mechanics defies our ordinary, common-sense intuitions about cause, effect, and the flow of time itself. The strange behavior revealed by the double-slit experiment points toward one of quantum physics' central, defining principles, called superposition. In classical physics, an object always has a single, definite set of properties at any given moment. A coin, however it happens to be resting, is either heads or tails, never both, whether or not anyone is currently looking at it.
Quantum particles behave very differently.
Before being measured, a quantum particle can exist in a superposition, a genuine, simultaneous combination of multiple possible states, rather than secretly occupying just one of those states while merely being unknown to an outside observer. An electron, for instance, can exist in a superposition of spinning in two opposite directions at once, not as a hidden coin flip whose outcome we simply haven't checked yet, but as a genuinely unresolved combination of both possibilities existing together, mathematically and physically, until a measurement forces the system to settle into one definite outcome or the other. This distinction, between genuine quantum uncertainty and simply not yet knowing a predetermined answer, was the subject of intense debate throughout the 20th century, and a series of ingenious experiments eventually confirmed that quantum superposition really does reflect a fundamentally different, non-classical kind of existence, rather than merely describing our own incomplete knowledge of some hidden,
already determined reality. Superposition is not confined to exotic laboratory conditions alone.
It underlies the strange interference pattern in the double-slit experiment, since a particle in superposition can, in some genuine sense, take multiple paths through space simultaneously, interfering with its own different possibilities, right up until a measurement forces it to commit to one single, definite outcome. It is one of the clearest illustrations of how deeply the quantum world differs from the sharp, definite, either-or logic that governs everything we experience directly with our own senses in daily life. Researchers have found ingenious ways to make superposition visible and useful well beyond the abstract mathematics used to describe it, including through a technique physicists call quantum interferometry, which relies directly on the wave-like interference between a particle's different simultaneous possibilities within a superposition.
These techniques have practical applications extending well beyond pure theoretical curiosity, including some of the most precise measurement instruments ever built by human engineers. The Laser Interferometer Gravitational Wave Observatory, better known as LIGO,
which made history in 2015 by directly detecting gravitational waves for the first time, relies on extraordinarily precise interference measurements sensitive enough to detect distance changes thousands of times smaller than the width of a single proton, a level of precision that pushes right up against the fundamental limits imposed by quantum uncertainty itself, requiring physicists to develop specialized quantum techniques specifically to work around these limits and achieve the instrument's remarkable sensitivity. Superposition, in other words, is not merely a strange theoretical curiosity confined to electrons and photons in laboratory experiments, but an active, essential working principle behind some of the most sophisticated scientific instruments ever constructed. No image from quantum physics has entered popular culture more thoroughly than Schrödinger's cat, the thought experiment involving a cat sealed inside a box alongside a radioactive source with a 50% chance of triggering a mechanism that releases poison, leaving the cat, according to a strict, literal application of quantum superposition, in a state that is somehow simultaneously alive and dead until the box is opened and the situation is finally observed. What often gets lost in the popular retelling of this famous scenario is that physicist Erwin Schrödinger did not propose it in 1935 to illustrate a genuine, literal feature of reality he believed to be true. He proposed it specifically as a criticism, a deliberately absurd thought experiment designed to highlight what he considered a troubling, unresolved problem and how physicists of his time were interpreting quantum mechanics. Schrödinger was pointing out that if quantum superposition genuinely applies at every scale, including large, everyday objects like cats, then the theory seems to produce an obviously nonsensical result, since we never actually observe cats, or coins, or apples existing in some blurred, simultaneously alive and dead or heads and tails state in ordinary macroscopic life. This puzzle, now known as the quantum measurement problem, remains genuinely unresolved even today, with physicists holding several competing, seriously considered interpretations about what actually happens as quantum effects scale up from tiny particles to the large, familiar objects of everyday experience, including cats, coins, and human beings. Some physicists favor an interpretation in which the act of measurement genuinely, physically causes superposition to collapse into one definite outcome. Others favor a very different interpretation, called the many worlds interpretation, in which every possible outcome actually occurs, each in its own separate, branching universe, with no true collapse happening at all, merely an ever-expanding tree of coexisting realities. Schrödinger's cat, in other words, was never meant to describe an actual, literal cat's actual, literal fate. It was meant to expose a genuine crack in our understanding of nature that physicists are, remarkably, still working to fully resolve nearly a century later. There is a particularly fascinating modern chapter to this story that Schrödinger himself never lived to see. In recent decades, physicists have actually succeeded in creating genuine superposition states in objects considerably larger and more complex than a single electron or photon, gradually pushing the boundary of what was once considered purely theoretical territory further and further toward the macroscopic, everyday scale Schrödinger's original thought experiment was concerned with. Researchers have placed tiny mechanical resonators, and even relatively large molecules containing hundreds of atoms, into genuine, experimentally verified superposition states, demonstrating that quantum superposition is not strictly confined to the smallest imaginable particles after all, but can, under sufficiently careful, controlled laboratory conditions, extend to progressively larger and more complex systems than physicists once assumed possible. No one has come remotely close to placing an actual living cat into genuine quantum superposition, and most physicists believe the practical and theoretical challenges involved in doing so, particularly the difficulty of protecting such a large, complex, warm biological system from decoherence, may make this forever impossible in practice even if it isn't strictly forbidden in principle. Still, this ongoing research into progressively larger superposition states represents one of the most active and genuinely exciting frontiers in modern experimental quantum physics, directly engaging with the very question Schrödinger's famous thought experiment was originally designed to provoke. Among all of quantum physics' strange phenomena, few have generated as much genuine bewilderment, even among the field's own founding physicists, as quantum entanglement. When two particles become entangled through a specific kind of interaction, their properties become linked in a deeply intimate way, such that measuring a property of one particle instantly determines the corresponding property of the other, regardless of how far apart the two particles happen to be, even if they are separated by the entire width of the observable universe. This correlation is not merely statistical coincidence, the way two people might happen to be wearing the same color shirt by chance. Careful experimental tests, closing loophole after loophole that skeptics proposed over decades, have confirmed that entangled particles are linked in a way that cannot be explained by any hidden, predetermined property the particles secretly carried with them from the very beginning of their entanglement. Albert Einstein, along with physicists Boris Podolsky and Nathan Rosen, found this implication deeply troubling in a famous 1935 paper, since it seemed to require information traveling between the two particles faster than the speed of light, violating one of the deepest and most well-established principles in all of physics, Einstein's own theory of relativity. Einstein famously derided the phenomenon as spooky action at a distance, believing it revealed quantum mechanics to be an incomplete theory rather than a genuinely accurate description of nature. Decades later, physicist John Stuart Bell developed a mathematical test, now called Bell's theorem, capable of experimentally distinguishing between Einstein's preferred explanation, involving hidden predetermined properties, and the genuine quantum explanation involving true entanglement. When these experiments were finally performed, beginning in the 1970s and refined with increasing rigor through the following decades, the results consistently favored quantum mechanics over Einstein's proposed alternative, a body of work recognized with the 2022 Nobel Prize in Physics, awarded jointly to Alan Aspect, John Clauser,
and Anton Zeilinger for their experimental confirmation of entanglement's genuinely strange, non-local character.
Importantly, entanglement does not actually allow faster-than-light communication of usable information, since the outcome of any individual measurement remains genuinely random, and the correlation between entangled particles can only be confirmed after the fact, by comparing results through conventional, light-speed-limited communication, preserving relativity's core principles even while entanglement itself remains every bit as strange and unsettling as Einstein originally found it. Entanglement has moved well beyond a purely theoretical curiosity in recent years, forming the practical foundation of an entirely new field called quantum cryptography, which uses the strange, delicate nature of entangled particles to create genuinely secure communication channels. Because measuring an entangled quantum particle inevitably disturbs its delicate state in a detectable way, any attempt by an eavesdropper to intercept and read a quantum encrypted message leaves behind an unmistakable, detectable trace, alerting the legitimate communicating parties that their communication has been compromised, a level of built-in security fundamentally impossible to achieve using conventional, classical encryption methods alone. Several countries and research institutions have already successfully demonstrated quantum key distribution networks operating across genuinely impressive distances, including satellite-based entanglement experiments conducted by Chinese researchers that successfully distributed entangled photon pairs between ground stations separated by well over 1,000 kilometers, representing one of the clearest,
most tangible real-world applications of a phenomenon Einstein himself once considered too strange and troubling to represent an accurate, complete description of physical reality.
In 1927, physicist Werner Heisenberg introduced one of the most profound and frequently misunderstood ideas in all of quantum physics, now known as the uncertainty principle. In its simplest form, the principle states that certain pairs of physical properties, most famously a particle's exact position and its exact momentum, cannot both be known with perfect precision simultaneously. The more precisely you measure one of these properties, the less precisely the other can, even in principle, be known. What makes this idea so frequently misunderstood is the assumption that it merely reflects a limitation of our measuring instruments, a kind of clumsy imprecision we might eventually engineer our way past with sufficiently advanced technology.
This is not what Heisenberg's principle actually describes.
The uncertainty is not a practical limitation of measurement technique. It is a fundamental, built-in feature of reality itself, meaning a particle genuinely does not possess a perfectly precise position and a perfectly precise momentum simultaneously, not merely that we are technically unable to measure both at once. This distinction matters enormously, because it reflects something deep about the actual, underlying nature of quantum reality rather than a simple gap in human engineering capability. The uncertainty principle arises directly from the same wave-like character of matter discussed earlier in tonight's episode, since a wave that is very precisely localized in space, meaning tightly confined to a small, specific region, must necessarily be composed of a wide range of different wavelengths blended together, and wavelength is directly related to momentum in quantum mechanics, meaning a very precisely localized wave inherently carries a correspondingly wide spread, or uncertainty,
in its momentum, and vice versa.
This is not a flaw in the theory or an embarrassing gap physicists hope to eventually close. It is one of quantum mechanics' foundational, mathematically rigorous features, with real, measurable, technologically important consequences, including placing fundamental limits on the precision achievable by extremely sensitive scientific instruments, and playing a central role in modern quantum computing and quantum cryptography research being actively developed today. Heisenberg developed this principle during an unusually intense and productive period in his early career, working through much of it in relative isolation on the remote island of Helgoland in the North Sea, where he had retreated in 1925 partly to escape a severe bout of hay fever, and where, according to his own later recollections, he experienced a genuine sense of both excitement and disorientation as the strange new mathematics of quantum mechanics began falling into place around him for
the first time.
The uncertainty principle he formalized 2 years later carries consequences that extend well beyond position and momentum alone, applying more broadly to several other pairs of related physical properties throughout quantum mechanics, including a similarly fundamental relationship between energy and time, which states that a quantum system's energy cannot be known with perfect precision unless that system is observed over an infinitely long duration, a limitation with genuinely important consequences for understanding phenomena including the natural, finite lifetimes of unstable particles and excited atomic states throughout the universe, tying this seemingly abstract mathematical principle directly to concrete, measurable physical behavior observed throughout nature. Imagine rolling a ball toward a hill too steep and too tall for it to ever climb over using the momentum you gave it.
In the ordinary, everyday world governed by classical physics, that ball simply cannot reach the other side.
It lacks the energy required, and no amount of weighting will change that basic fact.
In the quantum world, something genuinely stranger can happen.
A quantum particle approaching an energy barrier that should, by classical physics, be completely impossible to overcome has a small but real, measurable probability of appearing on the other side anyway, not by somehow gaining the extra energy needed to climb over the barrier, but by effectively passing straight through it, a phenomenon called quantum tunneling.
This is not simply a theoretical curiosity confined to physics textbooks.
Quantum tunneling has real, measurable, and in some cases enormously consequential effects throughout nature and modern technology. It is the mechanism that allows nuclear fusion to occur inside the core of the Sun at temperatures and pressures that would otherwise, according to classical physics alone, be insufficient for hydrogen nuclei to overcome their mutual electromagnetic repulsion and fuse together, meaning tunneling is quite literally one of the reasons stars are able to shine at all, our own included. Closer to home, quantum tunneling is also the underlying principle behind the scanning tunneling microscope, an instrument capable of imaging individual atoms on a material's surface by measuring the tiny tunneling current that flows when a sharp probe is brought extremely close to, but not actually touching, the surface being studied. Tunneling also plays an essential role in modern computer processors, where engineers must carefully account for it as transistors shrink to increasingly minuscule scales, since electrons in extremely small components can occasionally tunnel through barriers that were specifically designed to contain them, a genuine engineering challenge in the ongoing effort to make computer chips smaller and more powerful with each passing generation. Quantum tunneling has also found an ingenious and somewhat unexpected medical application through a technology called the scanning tunneling microscope's close cousin, the atomic force microscope, and related tunneling-based devices now used in certain specialized diagnostic tools. Beyond direct medical imaging, tunneling plays an essential and often overlooked role in a significant portion of Earth's own naturally occurring radioactivity, since a common form of radioactive decay called alpha decay, in which an unstable atomic nucleus emits a small particle and transforms into a different, lighter element, relies directly on quantum tunneling to occur at all. Classical physics alone would predict that the alpha particle involved simply doesn't have enough energy to escape the powerful nuclear forces holding it inside the parent nucleus, yet tunneling allows a small but genuinely real probability for the particle to appear outside the nucleus anyway, a process happening constantly throughout naturally radioactive materials found throughout the Earth's crust, quietly demonstrating that this strange quantum phenomenon isn't confined to stars, laboratories, or advanced electronics alone, but has been shaping the geological and radioactive character of our own planet since long before any human being existed to study or even wonder about it. For decades, quantum superposition and entanglement existed primarily as fascinating but largely abstract features of nature, studied mostly for the sake of understanding reality more deeply rather than for any obvious practical application. That has changed dramatically in recent years, as engineers and physicists have learned to harness these same strange quantum properties to build an entirely new category of computing device. Ordinary computers, including the device you might be using to watch this very video, process information using bits, each one existing in one of exactly two definite states, either a 0 or a 1, with every calculation ultimately reducible to enormous numbers of these simple binary choices performed in rapid sequence. Quantum computers instead use quantum bits, or qubits, which take direct advantage of superposition, existing in a combination of both 0 and 1 simultaneously, rather than being locked into one definite value the way an ordinary bit is. When multiple qubits become entangled with one another, the total number of simultaneous states the system can represent grows exponentially with each additional qubit added, offering, for certain very specific types of mathematical problems, the theoretical potential for computational power that would be effectively impossible for even the most powerful classical supercomputers to match. It's worth being genuinely precise about where this technology actually stands today, since popular coverage sometimes overstates current capabilities considerably. Quantum computers built so far remain extremely limited in practical scope, are notoriously difficult to keep stable, since the delicate quantum states involved are easily disrupted by even tiny amounts of environmental interference, a problem researchers call decoherence, and are not, at present, a faster general-purpose replacement for ordinary computers in most everyday tasks. Their genuine promise lies instead in a narrower set of specific problems, including certain types of cryptography, complex molecular simulation relevant to drug discovery and materials science, and specific categories of optimization problems, areas where researchers believe quantum computers may eventually offer capabilities that no amount of classical computing power could ever realistically achieve, even with unlimited time and resources. The race to build increasingly capable quantum computers has become a genuinely global scientific and industrial effort, with major technology companies, national governments, and university research groups all investing enormous resources into overcoming the considerable engineering challenges involved. Different research teams have pursued genuinely different physical approaches to actually building stable qubits, including using superconducting circuits cooled to temperatures colder than deep space, individually trapped ions suspended and manipulated using precisely tuned laser beams, and photons of light itself carefully guided through specialized optical circuits, each approach carrying its own particular advantages and its own particular engineering difficulties. In 2019, researchers at Google announced what they described as a demonstration of quantum supremacy, performing a specific, deliberately chosen calculation on a quantum processor that would have taken the world's most powerful classical supercomputer an estimated 10,000 years to complete, in a task the quantum processor accomplished in a matter of minutes, a milestone that generated considerable excitement, alongside some genuine scientific debate about the practical significance of the specific, narrowly defined task chosen for the demonstration, illustrating both the real, tangible progress being made in this field and the genuine complexity involved in fairly evaluating exactly how significant any particular quantum computing milestone actually is. One of the most persistent and widespread misunderstandings surrounding quantum physics involves the idea, popularized considerably by loose, informal science communication, that human consciousness itself is somehow required to collapse a quantum superposition, as though particles are specifically waiting for a conscious mind to look at them before committing to a definite state.
This is not what mainstream physics actually concludes from the relevant experiments.
What genuinely causes a quantum system to lose its delicate superposition is interaction with its surrounding environment, a process physicists call decoherence, which can be triggered by an enormous range of interactions, including collisions with air molecules, exposure to stray photons of light, or contact with any sufficiently large, complex system capable of recording information about the quantum particle state, none of which require a conscious human mind to be present or paying
attention at all.
In the double-slit experiment discussed earlier tonight, placing a detector at the slits disrupts the delicate superposition not because a human being consciously reads the detector's readout, but because the detector itself physically interacts with the particle in a way that records which path information, and that physical interaction alone,
entirely independent of whether any conscious observer ever actually looks at the resulting data, is sufficient to destroy the interference pattern.
Physicists studying decoherence have demonstrated this distinction clearly through experiments in which detectors record which path information without any human ever checking the results in real time, confirming that the interference pattern still vanishes under these conditions, proving conclusively that the disruption comes from the physical interaction itself rather than from conscious observation specifically. This distinction matters enormously for correcting one of the most widespread popular misconceptions about quantum physics, since claims about consciousness directly shaping physical reality, while genuinely fascinating as philosophical speculation, considerably overstate what the actual physics and the actual experimental evidence genuinely support. The confusion around this topic has a genuinely understandable historical origin worth mentioning, since it did not emerge from nowhere. Some of the earliest interpretations of quantum mechanics developed in the mid-20th century, including certain formulations associated with physicists like Eugene Wigner, did seriously entertain the possibility that consciousness might play some special, privileged role in quantum measurement, and these ideas circulated seriously within parts of the physics community for a time before more careful subsequent experimental and theoretical work involving decoherence gradually clarified that ordinary physical interaction, entirely independent of consciousness, is fully sufficient to explain the collapse of superposition observed in every experiment conducted to date. This historical origin helps explain why the consciousness-based interpretation, though now considered outdated and unsupported by the overwhelming majority of practicing physicists, continues to circulate so persistently within popular science communication and, at times, within various forms of spiritual or self-help literature that borrow quantum terminology without engaging seriously with the actual, considerably less mystical physics involved. Understanding decoherence as the genuine underlying mechanism offers a clearer, more physically grounded picture, one that remains genuinely strange and fascinating in its own right without needing to invoke consciousness or mysticism to feel appropriately mysterious. As quantum physics developed further throughout the 20th century, physicists eventually arrived at an even deeper, more fundamental description of reality than particles and waves alone, called quantum field theory. In this framework, what we casually call particles, electrons, photons, quarks, and the rest, are not truly the most fundamental building blocks of the universe at all. Instead, physicists now understand reality as being built from quantum fields, continuous entities that permeate all of space, with what we perceive as individual particles actually representing localized excitations, or ripples, within these underlying fields, somewhat analogous to how a single wave rising on the ocean's surface is not a separate, independent object from the ocean itself, but rather a temporary, localized disturbance within the larger continuous body of water. An electron, in this deeper description, is understood as a small, quantized ripple in what physicists call the electron field, which exists everywhere throughout space, even in regions where no actual electron currently happens to be present. This reframing, while considerably more abstract and mathematically demanding than simply picturing tiny particles bouncing around like miniature billiard balls, has proven extraordinarily successful, forming the foundation of the standard model of particle physics, the remarkably accurate and thoroughly tested framework describing all of the known fundamental particles and forces, with the notable exception of gravity, which continues to resist full incorporation into this same quantum framework despite decades of dedicated effort by some of the finest theoretical physicists in the world. Quantum field theory also predicts a genuinely strange consequence directly relevant to the very fabric of empty space itself, namely that what we casually call a vacuum, seemingly empty space entirely devoid of any matter or energy, is not actually empty at all in the deepest quantum sense, but is instead constantly, briefly alive with what physicists call virtual particles, fleeting fluctuations that spontaneously appear and disappear throughout even the most perfectly empty regions of space. A phenomenon with genuine, experimentally measurable consequences that we'll explore further in just a moment. The persistent difficulty in fully incorporating gravity into the same quantum field framework, mentioned only briefly a moment ago, represents one of the deepest, most actively pursued open problems remaining in all of modern theoretical physics. Every other known fundamental force, electromagnetism, and the strong and weak nuclear forces governing behavior deep within the atomic nucleus, has been successfully described using this quantum field approach, unified together within the standard model with extraordinary experimental precision, confirmed across decades of careful particle physics experiments. Gravity alone continues to resist this same treatment, remaining most successfully described instead by Einstein's earlier theory of general relativity, an elegant but fundamentally classical, non-quantum framework that treats gravity not as a field or particle interaction at all, but as the geometric curvature of spacetime itself, caused by the presence of mass and energy. Reconciling these two extraordinarily successful but seemingly incompatible frameworks, quantum field theory on one hand and general relativity on the other, into a single, unified theory of quantum gravity remains one of the most significant, unsolved challenges in physics, motivating decades of theoretical work on candidate approaches including string theory and loop quantum gravity, neither of which has yet achieved anything close to the kind of definitive experimental confirmation that has validated other areas of quantum physics discussed throughout tonight's episode. Building directly on the quantum field concept introduced a moment ago, one of the more genuinely startling implications of modern quantum physics concerns the true nature of a vacuum, the seemingly empty space remaining once every last particle of matter has been carefully, thoroughly removed. Classical physics assumed that a true vacuum represented complete, absolute nothingness, an empty stage with no activity of any kind occurring within it. Quantum field theory paints a very different, considerably stranger picture. Because of the uncertainty principle discussed earlier tonight, energy itself cannot be perfectly, precisely zero everywhere at every single instant, even within what we call empty space, meaning tiny, extremely short-lived pairs of virtual particles and their corresponding antiparticles are constantly, spontaneously popping into brief existence throughout the vacuum, only to annihilate each other again almost instantly afterward, a process happening continuously, everywhere, all the time, even within the seemingly empty space surrounding you right now as you listen to this. This might sound like an abstract mathematical curiosity with no genuine, testable physical consequence, but physicists have actually confirmed this strange vacuum activity experimentally, through a genuinely remarkable phenomenon called the Casimir effect, first predicted theoretically by physicist Hendrik Casimir in 1948 and subsequently confirmed through careful laboratory experiments. When two uncharged, perfectly parallel metal plates are placed extremely close together in a vacuum, with only an extremely narrow gap separating them, the plates experience a small but genuinely measurable attractive force pulling them together, arising because the narrow gap between the plates restricts which virtual particle fluctuations can occur within that confined space compared to the essentially unrestricted space surrounding the plates on the outside, creating a subtle pressure imbalance that pushes the plates gently toward one another. This effect has been measured with increasing precision across numerous careful experiments since it was first predicted, offering direct, concrete experimental evidence that empty space genuinely does contain this constant, restless quantum activity, rather than representing the simple, static nothingness that classical intuition would otherwise lead us to expect. This same underlying vacuum activity connects to one of the more genuinely puzzling open questions currently facing modern cosmology, involving the accelerating expansion of the universe itself. When physicists attempt to calculate the theoretical energy density that this constant quantum vacuum activity should, according to quantum field theory, contribute to space itself, and compare that calculation to the actual observed energy density associated with dark energy, the mysterious force apparently responsible for the universe's observed accelerating expansion, the theoretical prediction and the actual observed value differ from one another by an almost unimaginably large factor. Often described as the worst theoretical prediction in the entire history of physics. This enormous, still genuinely unresolved discrepancy, sometimes called the cosmological constant problem, remains one of the deepest open puzzles connecting quantum field theory to our broader understanding of the universe's large-scale structure and ultimate fate, a vivid reminder that even with everything modern physics has successfully explained about the strange quantum realm, genuinely fundamental mysteries remain, patiently waiting for some future physicist to finally untangle them. We close tonight's exploration with a fact that often surprises people most of all, given how consistently quantum physics gets framed, understandably, as a realm relevant only to exotic laboratory conditions and subatomic particles far removed from ordinary daily experience. In reality, quantum mechanical effects are already quietly embedded throughout an enormous range of everyday technology most of us rely on constantly without ever considering the strange physics operating underneath the surface. The transistors inside every computer, smartphone, and modern electronic device rely fundamentally on quantum mechanical principles governing how electrons behave within semiconductor materials, meaning quantum physics is not some distant, abstract curiosity but the actual, working foundation underneath nearly the entire modern digital world. The laser, invented in 1960 and now used in everything from barcode scanners and fiber optic internet cables to surgical medical equipment and simple laser pointers, depends directly on a specifically quantum mechanical process called stimulated emission, first theoretically predicted by Einstein decades before the technology to actually build a working laser had been developed. Magnetic resonance imaging, the MRI machines used throughout modern medicine to produce detailed images of the body's internal structures without any need for invasive surgery, relies directly on a quantum mechanical property of atomic nuclei called spin, manipulated and measured using powerful magnetic fields according to principles developed directly from quantum theory. Even something as seemingly unrelated to physics as photosynthesis, the process every green plant on Earth uses to convert sunlight into usable chemical energy, appears, according to more recent research, to involve genuine quantum mechanical effects, including a limited, carefully studied form of quantum coherence that may help plants transfer captured solar energy through their cellular structures with remarkable efficiency. Quantum physics, in other words, was never really confined to strange, distant laboratory experiments involving individual electrons or exotic subatomic particles alone. It is, quietly and almost invisibly, one of the foundational layers of reality that your entire everyday life, right down to the device you may be using to hear these very words, has been resting upon this entire time, largely unnoticed, the way the deepest layers of any structure are rarely visible from where you happen to be standing. Global positioning system technology, relied upon constantly by smartphones, cars, and countless other devices for accurate navigation, offers one final, particularly elegant example worth mentioning, since it depends not on quantum mechanics alone but on a genuinely fascinating interplay between quantum physics and Einstein's theory of relativity working together. The atomic clocks aboard GPS satellites, which must maintain almost unimaginably precise timekeeping for the entire system to function accurately, rely directly on quantum mechanical transitions within atoms, the same kind of discrete, quantized energy jumps discussed at the very beginning of tonight's episode, to define time with extraordinary precision. At the same time, engineers must also carefully correct these same atomic clocks for small but genuinely significant relativistic effects, since satellites experience time passing very slightly differently than clocks here on Earth's surface, due to both their high orbital speed and their distance from Earth's gravitational field. Without carefully accounting for both the underlying quantum mechanics of atomic timekeeping and the relativistic corrections layered on top of it, GPS navigation would accumulate significant, compounding errors within just a matter of hours, drifting increasingly further from accuracy with each passing day, a beautifully concrete, everyday example of how two of physics' greatest 20th century revolutions, quantum mechanics and relativity, work together quietly, continuously, and almost entirely unnoticed, every single time you check directions on your phone. Tonight we travel through one of the strangest and most genuinely mysterious layers of reality science has ever uncovered. We began with the simple, disorienting discovery that the universe is not smooth and continuous at its smallest scale, but grainy, made of discrete quanta rather than an unbroken flow. We explored how light, and eventually all matter, seems to exist as both wave and particle simultaneously, and how the famous double-slit experiment revealed that the simple act of observation appears to shape which version of reality actually shows up. We sat with superposition, the strange quantum habit of existing in multiple states at once until something forces a single outcome to emerge, and we clarified what Schrödinger's cat was actually meant to illustrate, a challenge rather than a literal claim about living, breathing cats. We touched entanglement, the spooky, non-local connection Einstein himself found deeply troubling, and Heisenberg's uncertainty principle, a genuine limit woven into the fabric of reality rather than a simple flaw in our instruments. We passed through quantum tunneling, the strange mechanism quietly powering the sun itself, and glimpsed how today's engineers are learning to harness superposition and entanglement inside real, working quantum computers. We gently corrected one of the field's most common myths, that consciousness itself is required to collapse a quantum state, and looked instead at quantum fields, the deeper, more fundamental layer beneath even particles themselves, and the strange, restless activity constantly rippling through what we casually call empty space. And we ended by noticing that none of this was ever truly distant or abstract at all, since quantum physics has been quietly, invisibly present inside your phone, your light bulbs, your medical scans, and even the leaves outside your window, this entire time. There is one final thought worth carrying with you as tonight's exploration comes to a close. So much of what unsettles people about quantum physics, when they first encounter it, is the sense that reality has somehow betrayed them, that the universe was supposed to make sense in a clean, orderly, predictable way, and instead turned out to be built from superposition, uncertainty, and strange, non-local connections that resist tidy explanation. But there is another way to hold this same information, one considerably gentler than betrayal. The universe was never obligated to match the small, familiar scale of human intuition, built as that intuition was for tracking predators, finding food, and navigating a world of medium-sized objects moving at ordinary speeds. That our minds can nonetheless reach down into a realm so utterly foreign to direct experience, and build careful, testable, remarkably accurate theories describing it anyway, is not evidence that reality has failed to make sense. It is evidence of just how far curious, patient attention can travel, even into places built on rules nothing in our evolutionary history ever prepared us to expect. If tonight's journey through the smallest layer of the universe was worth your time, a like, a subscribe, or a thought left below helps the Sleep Lab stay open for the next curious, sleepy mind who finds their way here. And if you're still awake, there's another story waiting just beyond this one, whenever you're ready for it. But for now, let your thoughts loosen the way a particle loosens into superposition, holding many soft possibilities at once, with nothing yet needing to be decided. Let your body settle. Let your breathing slow. And let the smallest, strangest layer of the universe carry you gently into rest. Sleep well. And good night.